The most important object in the Milky Way is almost invisible. Not distant, not tucked away in some unreachable age of the universe. It is here, in our own galaxy, buried behind curtains of dust and crowded starlight, sitting at the gravitational center of everything the Milky Way has become. And for almost all of human history, we had no direct way to see it. That is where the unease begins. We are built to trust surfaces. The bright thing feels important. The visible thing feels real. If something dominates a system, we expect it to announce itself. We expect radiance, size, presence, some natural visual authority. A center should look central. But the Milky Way does not obey that intuition. At the heart of our galaxy lies something with the mass of more than 4 million suns. It governs the motions of stars. It bends light. It sets the terms of an entire region of space. And yet, if you look toward the center of the Milky Way with ordinary eyes, you do not see a king. You see obstruction, a dense, glowing congestion of stars, gas, and dark lanes of interstellar dust. You see brightness without clarity. You see a place where vision becomes less trustworthy, not more. The deeper truth is almost offensive to common sense. The galaxy's center is ruled by something that had to be discovered, not by looking at it, but by watching what reality did around it. That changes the story immediately. Because this is not just a story about a black hole, it is a story about a failure in the way we expect reality to present itself. The thing that matters most does not necessarily shine. The thing that holds a structure together may not appear at its surface. Sometimes the deepest part of a system is detectable only by the strain it imposes on everything else. And once you see that, Sagittarius A star stops being just an exotic astronomical object. It becomes a wound in intuition. To appreciate how strange that is, it helps to begin with the scale we are actually talking about. The Milky Way is not a loose spray of stars. It is a rotating city of hundreds of billions of them, spread across a disk so wide that light itself takes about 100,000 years to cross it. Our sun lives far from the center, out in one of the galaxy's spiral arms, orbiting quietly in the suburbs. We are not stationed at the middle of the structure. We are inside it, off to the side, trying to understand the whole from a biased interior view. Imagine being born deep inside a forest so vast that you have never seen its edge, never climbed above its canopy, never even known what shape it has. All you know are trunks, patches of sky, gradients of density, the way some regions feel more crowded than others. That was our position in the galaxy for almost the entirety of our species' existence. The Milky Way was not an object out there. It was the environment around us. To locate its center at all was already a defeat for ordinary perception. And even after astronomy matured enough to understand that we lived inside a galaxy, the central region remained obscured. Between us and the core lies an enormous amount of interstellar dust, enough to block visible light so effectively that looking toward the center in ordinary wavelengths is like trying to study the bottom of a dark ocean through a storm-torn surface. The place of greatest interest was hidden not by distance alone, but by matter, not by emptiness, but by clutter. That matters, because it means the center did not first arrive in human understanding as an image. It arrived as a problem. There was something there. The galaxy's shape implied it. The motions of stars implied it. Later, strange emissions implied it. But the center did not yield itself in the straightforward way our instincts prefer. It resisted direct sight. It forced astronomers into a more disciplined posture. They had to stop asking, "What do we see?" and start asking, "What must be there for all of this to behave the way it does?" That is a more unsettling question. It is one thing to observe an object. It is another to infer an invisible sovereign from the distortions it imposes on everything around it. One feels like discovery. The other feels almost judicial. Reality is not offering itself freely. It is being cross-examined. And the closer astronomers came to the center, the stranger that cross-examination became. The central bulge of the Milky Way is crowded beyond ordinary imagination. Stars are packed there in densities that make our local stellar neighborhood feel almost empty. Gas clouds twist through the region. Magnetic fields thread through plasma. Explosions have happened there. Stellar winds collide there. Radiation scatters. Matter drifts inward, is heated, torn, redirected. It is not merely a bright place. It is a violent archive of accumulated gravity. Yet, buried inside that congestion is an even more concentrated reality, one so compact and so dominant that eventually every other explanation would begin to fail around it. But not yet. At first, all anyone truly had was suspicion. The center of the Milky Way was clearly not ordinary. It emitted unusual radiation. It sat behind so much obscuring dust that normal vision was crippled, and the motions in that region hinted at an organizing mass too severe to ignore. Yet, suspicion is not proof. Astronomy, at its best, is not impressed by what sounds dramatic. The universe has a habit of producing effects that look extraordinary until a quieter explanation appears. So, the central question could not be, is there a monster in the dark? The central question had to be, what is the least extravagant thing that can explain all of this? That is where the real tension lives. Because black holes have a peculiar place in the human imagination. They are famous enough to feel almost mythic, but their true scientific significance is less theatrical than people think. A black hole is not frightening because it is a cosmic predator waiting to lunge. It is frightening because it represents a place where the visible world ceases to be a reliable guide to the physical world. It is a case in which gravity becomes so extreme that light itself starts losing its negotiating power. A black hole does not just hide matter. It exposes a limit in the agreement between intuition and reality. And Sagittarius A star was going to force that confrontation at the center of our own galaxy. Not immediately, not cleanly, not with some dramatic first photograph that settled the matter in an instant. The truth would emerge more slowly than that, and in some ways more beautifully. It would emerge through patience, through new instruments, through wavelengths the eye can never see, and above all, through motion. Because when something refuses to reveal itself directly, the next best thing is to study what orbits it, what glows because of it, what bends under its presence, what cannot keep its path unless some hidden mass is pulling the strings. That is the first great reversal in this story. The center of the Milky Way was not discovered as a spectacle. It was discovered as an absence too powerful to remain hidden. And once that thought takes hold, the sky changes a little. The bright river of the Milky Way no longer feels like a serene band of stars crossing the night. It begins to feel like a mask, somewhere inside that glow, behind the dust, behind the crowding, behind the noise. There is a compact darkness heavy enough to organize a galaxy. Something nearly invisible is sitting in the place from which hundreds of billions of stars take their larger cue. The eye does not find it. Reality gives it away. And that raises the deeper question that will drive everything that follows. If the center of our galaxy is ruled by something we could not see, then how exactly? Do you prove the existence of the most important object in the Milky Way when the object itself refuses to shine? To answer that, astronomy first had to solve a more basic humiliation. Before you can uncover what rules the center of the Milky Way, you have to know where the center actually is. And that sounds easier than it was. From inside a galaxy, structure is not something you simply look at. It is something you reconstruct through bias, obstruction, and incomplete geometry. We were trying to identify the heart of a system while living deep inside one of its outer lanes, with dust cutting off our line of sight and perspective, distorting every large pattern. For a long time, the night sky encouraged the wrong kind of confidence. The Milky Way stretches overhead as a luminous band, and the band itself can create the illusion that the galaxy is something we already possess visually. But what we see from Earth is not a map. It is a slice from within. It is like standing inside a cathedral in total darkness with only a candle, then trying to infer the architecture from whichever columns happen to catch the flame. Brightness tells you something. It does not tell you enough. By the early 20th century, astronomers had begun to understand that the Milky Way was a vast stellar system and that the sun was not sitting near its center. That realization alone was a wound to human vanity. But even after that demotion, the exact center remained elusive. The problem was not just scale, it was concealment. Visible light does not travel cleanly through the crowded interior of the galaxy. Between our solar system and the central bulge lies an enormous quantity of interstellar dust, microscopic grains scattered through gas clouds, thin individually, devastating in aggregate. Over great distances, they absorb and scatter starlight so effectively that the central regions of the Milky Way are heavily veiled in ordinary wavelengths. The center is not absent from our view because nothing is there. It is absent because too much is there. That is one of the recurring cruelties in astronomy. Sometimes emptiness hides nothing. Sometimes fullness hides everything. The first serious clues came not from looking directly at the center, but from asking how the galaxy as a whole was distributed. If you cannot see the middle, you look for whatever still remembers its location. In the early 20th century, astronomers studying globular clusters found something decisive. These ancient, densely packed star clusters were not scattered around us at random. Their distribution pointed toward a region far from the Sun, in the direction of Sagittarius. It was one of the earliest strong indications that the true center of the Milky Way lay there, not near us, not anywhere our instincts had quietly placed it, but deep in a distant, dust-choked direction we could barely inspect. That was a turning point, though not yet a revelation. It gave astronomy a destination, not an answer. And, even then, the central region remained frustratingly opaque. Imagine being told that the most consequential room in a vast building lies behind a wall you cannot remove, and all you can do is listen for vibrations. That was the galactic center for decades. Astronomers knew where to point. They still did not know what they were truly pointing at. This is where the story begins to change character. It stops being a matter of simple observation and becomes a matter of translation. If visible light is blocked, then the universe must be approached in other languages. Longer wavelengths can pass through dust more effectively. Radio waves can do what visible light cannot. Infrared can enter regions that the eye would mistake for absence. The hidden center of the galaxy was not waiting for better eyesight. It was waiting for entirely different senses. That shift matters for more than technical reasons. It changes the philosophy of the search. In ordinary life, seeing feels like the final court of appeal. In astronomy, that privilege does not survive contact with reality. The universe is under no obligation to reveal itself in the narrow band of light human biology happens to call vision. The truth may be pouring toward us in wavelengths our bodies were never built to notice. The center of the galaxy was one of the clearest lessons in that discipline. If we wanted the truth, we would have to become less human in how we looked. And so, the search for the center became a search through obstruction. Radio astronomy began to expose structures and emissions hidden behind the dust. Infrared observations penetrated deeper into the crowded inner regions. The blurred glow of Sagittarius slowly thickened into a physical place rather than a symbolic direction. There were gas clouds there. There were compact sources of radiation. There were stars moving in an environment unlike the one around our sun. The central region was no longer just the geometric middle of the Milky Way. It was becoming a distinct physical regime, denser, harsher, and more compressed than intuition had prepared us for. But the more the dust thinned, the less comfortable the picture became. Because a true center is not just a location, it is a question about authority. What actually anchors this part of the galaxy? What dominates the motions there? What sets the scale of the intergravitational field? Those questions had been implicit from the beginning, but as the observations improved, they became impossible to avoid. The central bulge contained enormous numbers of stars. That alone could create strong gravitational effects. But there were hints that the story did not stop with a crowded stellar population. Something about the region felt too concentrated, too organized around a deeper point. At this stage, astronomy was still in dangerous territory. A hidden center can tempt the imagination into excess. Once a region becomes obscure enough, it starts attracting myth. Scientists are not immune to that. Exotic explanations acquire emotional momentum long before they acquire evidential legitimacy. So, the discipline had to remain severe. It was not enough to say that the center was strange. The universe is full of strange places. The real question was whether the strangeness pointed toward a particular kind of object. And that question could not yet be answered honestly. There is a difference between knowing that a city has a center and knowing what stands in its central square. The Milky Way's heart was beginning to emerge, but only in fragments. The evidence was still distributed across separate channels: the inferred geometry of the galaxy, the obscured stellar bulge, the radio emissions, the unusual density of matter, the growing sense that something compact might be embedded there. Each clue mattered. None of them alone could bear the full weight of the conclusion that would eventually come. So, the search tightened. Astronomers kept returning to Sagittarius because the galaxy kept returning them there. The central direction was not simply luminous. It was stubborn. It kept producing reasons not to look away. And as instruments improved, one fact became harder to ignore. Somewhere near the exact dynamical center of the Milky Way, hidden behind the dust, there appeared to be a remarkably compact source of radio emission. This did not settle anything, but it changed the pressure. Because a diffuse glow can belong to many things, a compact source is different. Compactness is already a form of accusation. It tells you that energy, mass, or both may be gathering into a smaller region than the comfort prefers. It narrows the space of explanations. It turns curiosity into scrutiny. And once that happened, the galactic center stopped being merely hard to see. It became hard to explain. What had begun as a geographical problem inside a dusty stellar system was turning into something more severe. The center was no longer just hidden. It was beginning to look concentrated in a way that demanded a reckoning, not yet with a black hole, not yet with certainty, but with the possibility that the Milky Way was organized around something far denser and far less visually cooperative than a normal cluster of stars. The galaxy had not revealed its ruler, but it had begun, almost reluctantly, to indicate the throne. And from that point on, the search was no longer just for a location in space. It was for the first object at the center that refused to behave like anything ordinary. It first appeared not as an image, but as a disturbance in the static. That is one of the most important tonal shifts in this entire story. By the time astronomy had learned to look toward the galactic center in radio wavelengths, the search had already become less visual, less intuitive, more forensic. The eye had been demoted. Dust had made that unavoidable. What mattered now was whether the hidden middle of the Milky Way would produce a signal compact enough, strange enough, persistent enough to separate itself from the general congestion of the inner galaxy. And in the direction of Sagittarius, something did. The central region of the Milky Way is noisy in almost every sense that matters. Gas clouds glow. Electrons spiral through magnetic fields. Supernova remnants leave scars. Dense clusters of stars crowd the background. Radiation bounces, scatters, accumulates. The area is not a clean laboratory. It is a compressed environment where many things can imitate importance for a while. So, the discovery problem was never just to detect emission. There was plenty of emission. The problem was to isolate something more concentrated than the rest, something that did not feel like part of the blur. This is where radio astronomy became decisive. Radio waves can travel through the obscuring dust that cripples visible light astronomy, which means they open a channel into regions that the ordinary sky conceals. But they bring a price with them. A radio map of the sky is not a familiar picture. It is assembled by instruments, reconstructed through timing, sensitivity, and spatial resolution. The deeper astronomy entered the radio universe, the less discovery resembled simple sight, and the more it resembled extracting structure from patterns that do not naturally look like the world. That mattered at the galactic center, because the truth there was not waiting in any humanly comfortable form. As radio observations of Sagittarius improved through the mid-20th century, astronomers identified an increasingly complex region filled with energetic phenomena. This larger radio bright area became known as Sagittarius A, a designation that sounds neat and singular but was, in reality, a bundle of overlapping structures and emissions projected into one of the busiest directions in the sky. There were extended components, there were thermal sources, there were hints of compactness within diffuse brightness. The region was alive, but not yet cleanly interpretable. Then resolution improved. That is one of the quiet revolutions in science. Reality often does not become stranger because the universe changes. It becomes stranger because our instruments become less forgiving. What first looked like one thing begins to separate into many. A haze turns into edges. A bright patch becomes a system of competing structures. The better you resolve the center of the Milky Way, the more it stops resembling a luminous blur and starts resembling an argument. And inside that argument, one component became impossible to ignore. In 1974, Bruce Ballack and Robert Brown identified an extremely compact radio source at the exact dynamical center of the galaxy. This object was smaller, denser in its emission, and more sharply localized than the surrounding radio structures. It was not the full region called Sagittarius A. It was a particularly compact source within it. To mark that distinction, it was given an asterisk. Sagittarius A star. The star in the name is not decoration. It is an admission that something had narrowed. Something in the center was no longer merely part of a crowded field. It had separated itself from the noise. That does not mean the conclusion arrived all at once. A compact radio source, by itself, is not a black hole. Astronomy does not get to leap from strange signal to ultimate explanation just because the destination is famous. Many energetic systems can emit radio waves. Dense star-forming regions can do it. Hot plasma can do it. Exotic but non-black hole configurations can sometimes mimic parts of the effect. Sagittarius. A star was not proof, but it was a wound in the safer explanations. Because compactness changes the emotional pressure of evidence. A large diffuse source can belong to a large diffuse process. A compact source makes a different kind of demand. It asks how much energy is being produced in how little space. It begins quietly counting the explanatory room left to you, and at the center of the Milky Way, where the surrounding environment was already gravitationally suspect. A compact source sitting at the exact middle of the entire galaxy did not feel like a coincidence. It felt like a concentration of consequences. Even then, astronomy remained disciplined. What made Sagittarius a star so scientifically potent was not that it instantly confirmed every dramatic idea people wanted to attach to it. It was that it persisted while alternatives became harder to stabilize around it. The source was compact. It was central. It was unusual. And perhaps most importantly, it was not behaving like an incidental feature of the background. It was beginning to look like the physical focal point around which the deeper story would have to be built. That is a subtle but crucial distinction. Science rarely advances by discovering a perfect answer in one moment. More often, it advances by finding a fact that the old world can no longer absorb. Sagittarius, a star, was becoming exactly that kind of fact. To feel the weight of this, it helps to step back from the technical language for a moment. Imagine entering a darkened concert hall after the performance has ended. The room is full of lingering sound, echoes, footsteps, faint electrical hum, scattered noise from every direction. Then somewhere in the darkness, one tone remains unnaturally pure, not loud, not theatrical, just too concentrated to belong to the rest of the room. You do not yet know what is making it, but the existence of that tone changes the space. It creates a center of suspicion. Sagittarius A star had that effect on the inner galaxy. The galactic center had long been a place of density and concealment. Now it also had a point, a localized source, a stubborn emission emerging from the same region where theory, geometry, and growing dynamical evidence all suggested some deeper concentration of mass should lie. The case was not closed. In some sense, it had only just begun, but the search was no longer wandering through a vague central brightness. It had found a target severe enough to keep returning to, and that changed the rhythm of the investigation. Before Sagittarius, a star, the center of the Milky Way was still partly a direction. After Sagittarius A star, it was increasingly an object of interrogation. Astronomers asked how large the source truly was. They asked how bright it was across different wavelengths. They asked how stable its emission remained over time. They asked whether interstellar scattering was making it appear larger than it really was. They asked what kind of physical process could occupy so little space at the exact center of the galaxy without immediately dissolving into something more ordinary. Each question cut away a little more comfort. The problem, however, was that the radio source alone still left room for caution. A compact source can accuse, but it cannot always convict. The galactic center was so complex that every claim had to survive not just intrigue, but attrition. If Sagittarius A star was to become more than a fascinating anomaly, it would need help from another line of evidence. It would need gravity itself to speak. That is when the deeper logic of the story begins to reveal itself. Radio astronomy found the whisper, but a whisper, no matter how strange, is still only part of a case. To understand whether Sagittarius A star was truly the long-suspected anchor of the Milky Way's heart, astronomers had to do something even harder than detecting a signal from behind the dust. They had to weigh the darkness. That meant turning away, in a sense, from the source itself, and toward the stars living dangerously close to it. Because a black hole can hide its surface, it cannot hide its influence. And once nearby, stars were tracked with enough precision, the central radio source would stop being merely unusual and start becoming intolerably specific. The question would no longer be whether something compact sat at the center of the galaxy. The question would become how any known thing other than a supermassive black hole could force stars to move the way they did. Sagittarius A star had entered astronomy as a signal. It was about to become a verdict. A verdict, though, is only meaningful if the alternatives have been given a real chance to survive. That is where this story becomes more severe than the usual public version. Popular science often makes black holes sound like they were embraced because they were dramatic. In reality, black holes become convincing only when everything less dramatic begins to break under pressure. Science does not reward the most thrilling idea. It rewards the one that remains standing after the quieter explanations have failed. And in the case of Sagittarius A star, the quieter explanations were not dismissed casually. They were cornered. At first, caution was not just reasonable, it was necessary. The center of the Milky Way is an environment so crowded, energetic, and physically complicated that it invites premature conclusions. A compact radio source at the galactic center was an extraordinary clue, but clues are not the same as causes. A dense star cluster could in principle produce strong gravity. A concentration of neutron stars, white dwarfs, stellar mass black holes, hot gas, or other compact remnants might mimic parts of the effect. If enough mass is packed into a small enough region, many different systems can look briefly persuasive. So the real question became ruthless in its simplicity. What is the least exotic thing that can explain all of this? That question is the opposite of sensationalism. It is a discipline against it. It forces every candidate explanation to do actual work, not just sound plausible, survive contact with the numbers. And the numbers were becoming less forgiving. The galactic center is not merely crowded in the everyday astronomical sense. It is compressed into a regime where mass, distance, and orbital speed begin accusing one another. If stars near the center are moving very fast, then something massive must be pulling on them. If that mass is concentrated into a very small volume, then whatever is there cannot be a loose stellar swarm spread comfortably through space. The denser the evidence became, the smaller the room left for ordinary explanations. This is where one of the most important intellectual habits in astrophysics comes into view. Sometimes you do not prove what something is first. You prove what it can no longer be. Could the center simply be a dense cluster of normal stars hidden behind dust? Not if the required mass is forced into too small a region. Normal stars take up space, they radiate, they collide, they evolve. Pack enough of them tightly enough, and the system becomes unstable, luminous in the wrong way, or short-lived on timescales that make its current existence improbable. Could it be a cluster of stellar remnants, white dwarfs, neutron stars, smaller black holes crowded together in the center? That sounds more sophisticated, and for a while such possibilities were taken seriously. After all, dead stars are compact. They can hide their light better than ordinary stars. They can in principle store a great deal of mass without announcing themselves visually. But this idea also runs into time. Dense clusters are not quiet forever. Objects gravitationally interact. They exchange energy. Some are flung outward, some spiral inward, some collide, some merge. in a cluster compact enough to imitate the inferred mass concentration near Sagittarius A star. Those interactions become brutal. Over time, the system tends to evaporate, collapse, or reorganize itself. A configuration dense enough to fake a supermassive black hole would generally not remain stable for the lifetime of the galaxy. And that is one of the coldest features of the black hole interpretation. It keeps winning not because it is grand, but because it is durable. A cluster of compact remnants may sound less extreme than a 4 million solar mass black hole, until you ask it to survive. Then the gentler explanation starts looking less believable than the harsher one. The universe does that sometimes. It punishes our preference for moderation. There is a deeper discomfort here. We are used to thinking that the extraordinary explanation should be the last resort. But in the presence of enough evidence, the black hole becomes not the extravagant answer, but the conservative one. The more tightly the central mass is constrained, the less scientifically responsible it becomes to cling to more intuitive alternatives. At some point, disbelief becomes less rational than surrender. Still, this surrender had to be earned, and earning it required more than broad claims about density. It required a conceptual shift in what a black hole really is. That phrase carries too much mythology. It suggests a kind of cosmic trapdoor, or a ravenous object with a personality, or a place where physics simply gives up. None of those impressions are useful here. They are emotionally loud, but mechanically weak. To understand why Sagittarius A star became the best explanation, we have to strip the metaphor away. A black hole is not, first of all, a thing in the ordinary sense. It is a region where gravity has become so concentrated that there exists a boundary beyond which light cannot return to the outside universe. That boundary is the event horizon. The crucial fact is not merely that matter falls in. Stars fall into other stars. Gas falls into planets. The crucial fact is that space-time itself becomes curved so severely that all future directed paths within that boundary lead deeper inward. Escape is not difficult. It is no longer physically available. That is already stranger than the popular metaphor allows. Because the event horizon is not a solid surface, it does not behave like a wall in space. An infalling object crossing it, if the black hole is large enough, would not necessarily strike anything at the boundary at all. Locally, the crossing could feel almost uneventful. The catastrophe is not that you hit a cosmic shell. The catastrophe is that the geometry has been altered so completely that the outside universe is no longer reachable as a future destination. Inside the horizon, outward stops being the kind of option our intuition assumes it is. This matters for Sagittarius A star, because once astronomers started inferring a mass of millions of suns confined to a region on the scale of the inner solar system, explanations based on ordinary matter began to look less like prudence and more like denial. A dense cluster of objects still presumes separate bodies occupying shared space. A black hole does not. It is the endpoint of concentration, not a heap of things crowded together, but a gravitational condition in which the old language of separate occupancy has already lost authority. That is why the black hole interpretation, once forced by the evidence, has a terrible elegance to it. It does not merely explain the compactness. It explains why compactness can exceed the stability limits of every more familiar system. And yet even here, honesty matters. To say that Sagittarius A star was becoming the best explanation is not to say every detail was finished. Science did not suddenly possess a complete portrait. There were still uncertainties about the precise accretion flow, the emission mechanisms, the environment around the source, the size of the emitting region, the rate at which matter was actually falling inward. Black holes are not explanatory magic. They solve some problems by creating others. Once you accept one, you inherit deeper questions about formation, feeding, radiation, and the behavior of matter in extreme gravity. But those later questions do not weaken the core conclusion. They strengthen its scientific character. A real theory does not end inquiry, it deepens it. By now, the logic was tightening into a shape that would not loosen again. Sagittarius. A star sat at the galactic center. It was remarkably compact. The surrounding region suggested an enormous concentration of mass. Ordinary alternatives grew less stable the harder they were asked to imitate those facts. The black hole hypothesis was no longer just an exciting possibility. It was becoming the only explanation severe enough to survive the demands being placed on it. Still, one problem remained. You can argue that some hidden mass must be there. You can even argue that only a black hole can remain viable. But argument becomes far more powerful when gravity is made visible in motion. The source itself could stay dark, compact, partially indirect. That was almost expected. The real breakthrough would come when nearby stars began to reveal, orbit by orbit, exactly how much mass was buried in that central darkness and how little space it had to occupy. That is the point where inference hardens into something close to confrontation. Because once a star races around an empty point in space at thousands of kilometers per second, the center stops feeling hypothetical. The darkness is no longer an interpretation laid over data. It becomes the only shape left that reality can take. And when that happened, Sagittarius A star stopped being merely the best explanation for the galactic center. It became the least avoidable fact in the Milky Way. Because once the stars began to tighten the case, the script could no longer rely on metaphor. Up to this point, the black hole has existed as a conclusion under pressure, the explanation that survives when the alternatives fail. But there is a danger here. The phrase black hole is so culturally overused that it can create a false sense of understanding. People hear it and feel that the mystery has been named. In truth, the naming only begins the harder task. If Sagittarius A star is a black hole, then what exactly does that mean physically? What kind of thing are we talking about when we stop using the dramatic language and keep only the mechanism? This is where the ground shifts from astronomy into ontology. A star is still legible to instinct. A planet is legible to instinct. Even a nebula, vast as it is, still belongs to a world where matter occupies space in ways the mind can picture. A black hole is different. It is one of the first places in physics where ordinary spatial intuition begins to betray us so badly that even simple explanations risk becoming misleading. The common image is easy enough. An object so dense that not even light can escape. That is not wrong. It is simply incomplete in exactly the wrong way. It makes the black hole sound like an unusually powerful vacuum cleaner, a kind of dark celestial machine with extra pulling force. But gravity does not work that way. A black hole with the mass of the sun does not pull more strongly than the sun from the same distance. Replace the sun with a black hole of equal mass, and Earth would still orbit at roughly the same speed and distance. The difference is not that the gravity becomes magically stronger everywhere. The difference is that the mass has been compressed into a region so small that space-time near it is driven into a regime ordinary matter never reaches. That distinction matters. A black hole is not just a lot of gravity. It is a condition in which mass is concentrated enough that there exists a boundary beyond which no signal can return to the outside universe. That boundary is the event horizon. And even that phrase horizon can mislead if we hear it too casually. It is not a surface in the familiar sense, not a shell, not a wall, not the crust of some hidden sphere. It is a limit in causality. That is a colder idea than most people expect. The event horizon is the place where escape ceases to be a future option, not because engines fail, not because friction drags you back, but because space-time is curved so severely that every physically allowed path forward continues inward, outside the horizon. You can still choose between futures that move away or toward. At the horizon and within it, that freedom is gone. The geometry itself has settled the matter. Inside, later, points deeper. That is the first truly destabilizing thing about black holes. They do not simply trap matter. They alter the relationship between direction and destiny. General relativity is the language that makes this intelligible. Einstein's theory tells us that gravity is not best understood as a force tugging on objects through empty space. It is the curvature of spacetime, created by energy and mass. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. In weak gravitational fields, this elegant description reduces to something close to Newton's older intuition. Apples fall, planets orbit, bridges remain standing. But as mass becomes more concentrated, the geometry stops behaving in ways our bodies were built to trust. And black holes are what happen when concentration is pushed so far that geometry outruns common sense. It helps to be careful here. There are several layers to the story, and if they are collapsed too quickly, the whole thing becomes either misleading or theatrically vague. First, there is gravitational collapse. A sufficiently massive star, after exhausting the fusion that once supported it, can no longer resist its own weight. The outer pressure that once pushed outward weakens. Gravity keeps pressing inward. Under the right conditions, no known force can permanently stop the collapse. Matter is driven past the point where neutron degeneracy or any other familiar pressure can stabilize it. An event horizon forms. From the outside, a black hole now exists. That sentence sounds neat. The reality beneath it is less comfortable. From the outside, the black hole can be described by only a few parameters: mass, spin, charge. Though astrophysical black holes are expected to have essentially negligible charge, this austerity is part of their strangeness. Take an ordinary star, a thing of seething complexity, internal gradients, nuclear reactions, magnetic structures, and layered matter. Push it through catastrophic collapse, and what remains outwardly describable becomes terrifyingly sparse. Not because nothing is there, but because so much detail has vanished behind a boundary the outside world cannot directly interrogate. A black hole is not just dense, it is information hidden by success. And yet the word hidden must also be handled carefully. The event horizon is not a curtain draped over a normal interior. It marks a region where classical relativity predicts that infalling matter continues inward toward a singularity, a place where the mathematical description of curvature diverges. But this is exactly where honesty matters most. Physicists do not treat the singularity as a fully understood physical object in the ordinary sense. It is better understood as a sign that our current theories have been driven past the domain where they can be trusted on their own. General relativity is extraordinarily successful, but without a complete quantum theory of gravity, the deepest interior of a black hole is not something science can yet describe with confidence. That uncertainty is not a weakness in the script. It is part of the truth the script should protect. The black hole is one of the few objects in science where the best established framework we possess points toward its own incompleteness. In other words, the most mathematically disciplined objects in the universe also lead us straight to the limits of what our mathematics can presently finish. That is why black holes feel larger than astronomy. They are not just exotic residents of the cosmos. They are stress tests for the human attempt to describe reality. Still, before getting lost in the interior, it is worth returning to the horizon, because that is where public intuition most often fails. If you were to fall toward a supermassive black hole like Sagittarius A star, the crossing of the event horizon would not necessarily resemble anything dramatic at the exact moment it occurred. No visible line hangs in space. No alarm sounds in the laws of nature. For a sufficiently large black hole, the tidal forces at the horizon itself can be surprisingly gentle compared with those near smaller black holes. Locally, you may notice nothing special at the instant of crossing. That is part of the terror. The decisive boundary in the structure may not feel decisive from within. The catastrophe is not always experiential at first. Sometimes it is geometric. Sometimes the deepest change is that your future has been silently narrowed in a way no sensation immediately announces. For a distant observer, the story looks different. Light emitted by something falling toward the black hole becomes increasingly redshifted and delayed. The object appears to slow, dim, and fade near the horizon, never quite seen to cross in any ordinary observational sense. This difference in perspectives is not a trick. It is part of the structure itself. A black hole does not merely challenge what happens. It challenges the assumption that there should be one simple way for all observers to narrate what happens. Even time loses the right to feel universal. Now bring this back to Sagittarius, a star. The reason all of this matters is that once astronomers began arguing that the Milky Way's center contains a black hole, they were not merely claiming that there was a very heavy hidden object there. They were claiming something far harsher. that the central anchor of our galaxy is a region where the structure of space and time has been driven into one of its most extreme known forms. A place that can be measured from outside, orbited from outside, imaged indirectly from outside, and yet never revealed in the ordinary sense because ordinary visibility itself stops being the right standard. The name black hole can make that sound familiar. It is not familiar. It only feels familiar because language has learned to say the words faster than intuition has learned to carry their meaning. That is why Sagittarius A star is so powerful as a subject. It forces us to stop using the black hole as a symbol and confront it as a mechanism, not a metaphor for mystery, not a cosmic villain, a gravitational fact, a region where geometry becomes the main event, and where the distinction between what exists and what can be seen begins to tear open. And once that is clear, a more precise form of shock becomes possible. Because the real scandal of Sagittarius A star is not merely that the object at the center of the Milky Way is a black hole. The real scandal is scale. This is not a collapsed star a few times heavier than the Sun. This is a concentration of more than 4 million solar masses in a volume small enough to make every surviving alternative explanation look unstable or absurd. The idea only fully lands when number and space are forced together. 4 million suns, one center, one darkness, one gravitational claim so compressed that the mind does not resist it because it is too large, but because it is too large in too little room. That is where the story sharpens next. Because once you stop thinking black hole in the abstract and start confronting the actual measured mass of Sagittarius A star, the issue is no longer merely what kind of object this is. The issue becomes how reality permits that much authority to live in so little space. Because scale, by itself, is almost never the real problem. The universe is full of large things. Stars are large, nebulae are large, galaxies are large. Even the numbers stop feeling abrasive after a while. Billions of stars, trillions of kilometers. Light years stacked into architectures too broad for the nervous system to hold at once. Vastness becomes familiar, surprisingly fast. The mind develops a numb, ceremonial relationship to it. You hear the quantity, you register the grandeur, but the shock does not stay alive. Sagittarius. A star is different because its power does not come from largeness alone. It comes from compression. 4 million suns is already an indecent number. Put that much mass into a loose stellar association, spread it through a broad volume, and the imagination can still negotiate. It will picture a crowded region, dense, perhaps violent, certainly important, but still legible. A place where many things share space. A place where the eye, given enough distance, could pretend there is still some ordinary relationship between amount and extent. That comfort fails here. The mass associated with Sagittarius, A star, is not distributed like a city. It is concentrated like a sentence with all the air removed, more than 4 million times the mass of the Sun, gathered into a region comparable in scale to the inner solar system. Not the size of the Milky Way's bulge, not the size of a star cluster in the familiar sense, a region on the order of Mercury's orbit, depending on exactly which boundary or characteristic scale you are describing, holding a gravitational authority that reorganizes the center of a galaxy. This is the real scandal. Not that the number is large, that the number is large in so little room. The Sun contains almost all the mass of our solar system. Everything else, planets, moons, asteroids, comets, is basically residue by comparison. And even the Sun, for all its size and violence, is still an ordinary star in structural terms. It is held up by pressure from nuclear fusion in its core. It glows because matter there is hot and dense enough to force hydrogen into helium. Outward pressure balances inward gravity. It occupies space with a kind of negotiated dignity. A star is gravity resisted. A black hole is what remains when that negotiation is over. But even that idea stays too abstract until the numbers harden. A black hole with the mass of the Sun would have an event horizon only a few kilometers across. Compress the Sun into a sphere roughly the size of a city, and you no longer have a star. You have crossed into a different category of existence. Now, multiply that mass by more than 4 million. The corresponding horizon scale grows, of course, but not into anything like a familiar astronomical body. You are still dealing with a compactness that feels hostile to common sense. Millions of suns translated into a gravitational region still small enough, in galactic terms, to vanish inside our ordinary intuition of empty space. That is why Sagittarius A star feels less like a heavyweight object and more like a betrayal of spatial expectation. We expect importance to occupy room. We expect dominance to present volume. We expect 4 million suns to look like something sprawling, bright, extended, hard to miss. Instead, the galaxy's deepest concentration of mass is hidden in a darkness small enough to let nearby stars appear to circle nothing. There is a special humiliation in that. The invisible point wins. This is where comparisons become useful, though only if handled with restraint. Say that Sagittarius A star has a mass of about 4.15 million suns, and the statement lands intellectually but not physically. Say that its horizon scale region would fit well within the orbit of Mercury, and suddenly the proportions turn abrasive. Mercury goes around the Sun at a distance of about 58 million kilometers. That is large to us, of course, but in astrophysical terms, it is intimate, domestic, a zone we treat as part of our own local mental furniture. To place millions of suns inside that kind of scale is not merely to state a fact, it is to force a contradiction into imagination. A galaxy anchored by something smaller than instinct thinks a galaxy's anchor should be. The result is not just astonishment, it is explanatory pressure. Because once you admit a mass concentration like that, almost every softer model starts suffocating. Separate objects need space between them. They interact, scatter, collide, exchange energy. If you try to hide 4 million solar masses in a cluster of ordinary bodies compressed into such a small region, the system becomes dynamically unstable or observationally implausible. If you try to make the cluster dark enough, dense enough, quiet enough, and long-lived enough, the requirements begin to turn against one another. Your alternative explanation starts behaving like a machine built to survive only on paper. A black hole, by contrast, absorbs the compactness without apology. That is part of its elegance. It does not rescue intuition. It eliminates the need for it. Still, there is another layer to this scale problem, and it is subtler: Sagittarius. A star is called a supermassive black hole, and the phrase can accidentally flatten the distinction that matters most. Stellar mass black holes, the remnants of massive stars, are already extreme objects, but supermassive black holes are not merely bigger examples of the same thing in the emotional sense. They occupy a different role in cosmic structure. They are not just endpoints of stellar death. They are long-term participants in galactic evolution, entangled with the formation of bulges, the heating of gas, the regulation of star formation, and the growth history of the galaxies around them. That does not mean we understand their origins cleanly. In fact, the origin of supermassive black holes remains one of the great unresolved stories in astrophysics. We know they exist. We know many galaxies host them. We know some reached enormous masses surprisingly early in cosmic history. But how the first seeds formed, and how some of them grew so quickly, is still an active area of research. Were the earliest seeds the remnants of the first generation of very massive stars? Did some form from the direct collapse of enormous primordial gas clouds? Did mergers and accretion do most of the later work? Almost certainly multiple channels matter, and the exact balance remains under investigation. That uncertainty is not a side issue. It sharpens the unease. Because Sagittarius A star is not only a concentration of mass, it is also a historical problem. A 4 million solar mass black hole at the center of our galaxy is a record of processes stretching back through billions of years of cosmic evolution. A kind of compressed archive of growth, feeding, collisions, and gravitational selection. The object is quiet today by the standards of the brightest galactic nuclei, but its current restraint should not be mistaken for simplicity. A calm black hole is not a simple one. It is merely one whose violence is not presently theatrical. and even its present calm becomes stranger under scale. If Sagittarius A star truly contains more than 4 million suns, why does it not blaze like a small quasar? Why does the center of our own galaxy not drown the inner sky in a constant inferno of accretion light? That question will matter later, because it becomes one of the most beautiful reversals in the whole story. The monster at the center is, by supermassive standards, underfed. It dominates without constantly announcing itself in the most obvious possible way. Yet, that later paradox only gains force once the mass itself has fully landed. 4 million suns. That phrase needs to remain heavy. Not because repetition creates drama, but because the number is the threshold beyond which Sagittarius A star stops sounding like an exotic object and starts sounding like a structural secret of the galaxy. A thing so massive that nearby stars cannot pretend it is absent. So compact that alternative explanations become increasingly unlivable. So hidden that the Milky Way's central truth had to be reconstructed from consequences rather than seen directly. This is the point where the concept becomes accusatory. If that much mass is truly there, then the stars closest to the center should be living in a gravitational regime, unlike anything in our local neighborhood. Their speeds should be enormous. Their paths should curve around an invisible center with a severity no loose cluster could easily fake. Their motion should begin to do what images still could not. It should weigh the darkness. And once astronomy became capable of tracking those stars precisely enough, Sagittarius A star stopped being merely a compact radio source with an alarming mass budget. It became something more intimate and more difficult to escape, a point around which individual suns were spending their lives in obedience. The black hole did not need to glow to declare itself. The orbits would do that more brutally than light ever could. And this is where the case stopped feeling theoretical. Up to now, Sagittarius. A star could still be held at a distance in the mind, a compact radio source, a likely black hole, a mathematically severe explanation for a hidden concentration of mass. All of that is powerful, but it still lives partly in abstraction. Numbers can be resisted. Concepts can be quarantined. Even the phrase 4 million suns can remain, for a while, a piece of disciplined language floating above physical intuition. Motion destroys that distance. Because once you watch individual stars whip around an apparently empty point in space, the darkness is no longer an idea. It becomes command. This was the next great revolution in the story of the galactic center. The transition from detecting Sagittarius A star as a source to measuring it as a gravitational master. Not by falling into it, not by seeing a bright boundary around it, but by watching nearby stars live under its authority year after year, orbit after orbit, as if tethered to something the eye still could not catch. That required patience bordering on devotion. The stars nearest the center of the Milky Way are hidden behind so much dust that visible light is almost useless, but infrared observations can penetrate far deeper into that obscuration, and by the late 20th century, improvements in infrared astronomy, adaptive optics, and high-resolution imaging began to make the central stellar environment measurable in a new way. The blur of the inner galaxy started to separate into individual stars, and once you can resolve stars as stars, you can do the most dangerous thing science ever does to a mystery. You can wait. This is one of the least glamorous and most devastating powers in astronomy. A single image can inspire, a time series can convict. If you watch the right objects for long enough, nature eventually stops hinting and starts testifying. Two major observing teams, working independently for years, helped bring this moment into focus. One, centered at UCLA under Andrea Ghez, the other, at the Max Planck Institute for Extraterrestrial Physics under Reinhard Genzel. Their work, and the work of many collaborators, transformed the galactic center from a region of suspicion into one of the most direct dynamical proofs in modern astrophysics. They were not looking for spectacle. They were measuring positions, velocities, orbital arcs, tiny shifts in starlight over time. They were doing something more powerful than revelation. They were allowing gravity to write its own affidavit. And at the center of that affidavit were the S stars. These are stars moving extraordinarily close to Sagittarius. A star, deep in the central parsec, in a gravitational environment so intense that their lives unfold at speeds and curvatures that would look almost pathological anywhere else in the galaxy. They are not arranged in neat, peaceful circles. They race along eccentric orbits, plunging inward and swinging back out, tracing paths that make the hidden mass at the center increasingly difficult to interpret as anything other than a supermassive black hole. One star in particular became famous for good reason: S2. It does not look famous in the ordinary sense. It is not a beacon, not a cosmic monument. It is simply one of the stars whose orbit was measured well enough, long enough, precisely enough to expose the central mass with humiliating clarity. S2 completes an orbit around Sagittarius, a star in about 16 years. That alone is astonishing. Think about what it means. Our sun takes roughly 230 million years to orbit the center of the Milky Way. S2, living in the deepest inner region, circles the galactic center in less time than it takes a human child to reach adulthood. The center is no longer a place. It is an engine of timing. At its closest approach, S2 comes within roughly a few light hours of Sagittarius A star and reaches speeds of several thousand kilometers per second, a few percent of the speed of light. Those numbers are not there for decoration. They are the pressure points of reality. A star does not move that fast around nothing. It does not swing through space on that kind of orbit because of a diffuse suggestion. Such motion demands a central mass both enormous and tightly confined. The orbit is the measurement. The speed is the accusation. And what the accusation said was brutal. The mass enclosed within S2's orbit had to be on the order of 4 million solar masses, not spread through a broad region, not loosely distributed among many comfortable bodies, packed into a volume so small that the remaining alternatives began to look less like scientific caution and more like evasive choreography. There is something almost embarrassing, from the perspective of human intuition, about how decisive this is. We tend to think reality reveals itself through appearance. But here, one of the deepest truths in our galaxy was forced into the open by kinematics. Not by direct sight, but by the curve of a stellar path over time. The black hole did not need to announce itself. A nearby star spent 16 years doing it for him. That is why these orbits matter so much emotionally, not just scientifically. They restore physical immediacy to something that might otherwise remain abstract. A compact radio source can still feel remote. But a star racing around an invisible center at millions of meters per second feels like obedience. It feels like the visible world bowing to an unseen law. And that, in a sense, is exactly what it is. The stars near Sagittarius. A star are not special because they are bright. They are special because they are compromised. Their trajectories have been drafted into service by a gravitational regime severe enough to betray the thing creating it. Every close orbit is a confession the center did not want to make voluntarily. Still, what makes this proof so beautiful is that it did not rely on one dramatic moment. It relied on accumulation, year after year. Measurements improved, the paths sharpened, the uncertainties narrowed. Proper motions became orbital solutions. Radial velocities joined positions. Three-dimensional motion emerged where once there had only been the impression of crowding. Astronomy did not leap to the answer. It cornered the answer by refusing to stop measuring. That patience altered more than the case for Sagittarius A star. It altered the emotional scale of the galactic center itself. Before, the black hole could still be imagined as a strange resident of a distant region. After the orbital work, the center became a governed space. You could feel hierarchy there, not metaphorically, dynamically. There was a point around which nearby stars were spending their lives in mathematically exact submission. And yet the deeper sting is that the point itself remained dark. This is one of the great humiliations black holes impose on perception. The more certain the central mass became, the less sight mattered as the privileged route to truth. If anything, the opposite was true. The eye remained stuck at the surface, while inference moved ahead into the architecture beneath. Ordinary visibility was not abolished, but it was demoted. What counted now was not what the center looked like, but what it forced the surrounding world to do. Reality became legible through obedience. That shift is larger than astronomy. It is almost philosophical. We are used to assigning reality to the tangible, the illuminated, the directly present. But Sagittarius A star reversed the order. The hidden thing was the physically decisive thing. The visible stars, for all their light, were playing supporting roles in the proof of something darker than they were. And the more precisely those roles were tracked, the more the old escape routes closed. Could a cluster of dark objects still explain the observations? In principle, one can always try to imagine distributions of matter that mimic a central black hole for a time. But by the time stars like S2 had been followed through substantial fractions of their orbits, the degree of confinement required became oppressive. Whatever sat at the center had to hold millions of solar masses within a volume so small, and do so stably, that the room for non-black hole models was collapsing. The stars were not just suggesting a mass concentration, they were compressing it into near inevitability. And then something even more important happened. Once the orbit of S2 was mapped with enough precision, the story was no longer only about mass. It became a chance to test the structure of gravity itself in the strong field environment near a supermassive black hole. That is the moment when the narrative changes register. Until now, the stars had been proving that something massive and compact sits at the center of the Milky Way. But if their motion could be measured finely enough, they might reveal not just how much mass is there, but whether space-time near that mass behaves the way Einstein said it should. The question was about to deepen, because Newton can guide you far, far enough. In fact, to describe most of the everyday celestial order human beings first learned to trust. But near Sagittarius, a star, Newton is not the final language. The orbits become too fast, the potential too deep, the geometry too severe. At that level, gravity stops being merely attraction and starts becoming structure. S2 had already helped weigh the darkness. Soon, it would help show that the darkness was bending time. And that is where the story stops being merely astronomical and becomes more intimate than comfort allows. A hidden mass at the center of the galaxy is already unsettling. It tells you that something nearly invisible can dominate an enormous system. It tells you that sight is not the highest court of reality. But there is still a way to keep that discomfort at a distance. You can treat it as a remote problem, a peculiar object in a strange environment, far from the scale of human experience, important in some abstract cosmological sense, but safely quarantined from the structure of daily intuition. General relativity ruins that distance. Because once the orbit of S2 was measured with enough precision, the question was no longer only whether Sagittarius A star was there. The question became whether the space-time around it behaved the way Einstein's theory predicted. Not in the weak gravitational fields where relativity quietly corrects Newton from a polite distance. Not in the familiar solar system regime where the effects are real but subtle. Here the field is stronger, the velocities larger, the geometry more compressed. If relativity was right, the star's light and motion would not merely reveal a hidden mass. They would reveal that time itself had become part of the evidence. That is a deeper kind of exposure. Newtonian gravity gives you attraction. It gives you orbits, accelerations, trajectories, and for centuries, that was enough to describe much of the visible order of the heavens with astonishing success. But Newton's universe still preserves something psychologically soothing. Space is a stage. Time is a shared background. Gravity acts across that stage, pulling bodies into relationship, elegant, powerful, and still close enough to instinct that the mind can rest inside it. Einstein took the rest away. In general relativity, gravity is not a force superimposed on space and time. Gravity is what space and time look like when mass and energy are present. Bodies move not because an invisible pull reaches out and drags them, but because space-time itself is curved, and motion follows that curvature. In gentle regimes, the difference can feel philosophical. Near Sagittarius, a star, it becomes operational. This mattered especially during S2's close approach to the galactic center. The star does not move in a placid circle. It plunges inward on a highly elliptical orbit, diving into a region where the gravitational field steepens and its speed rises to a few percent of the speed of light. That is fast enough and deep enough. That light emitted by the star should carry the signature of relativity itself. The photons climbing out of that gravitational well should lose energy. Their wavelengths should stretch. The star's spectrum should shift toward the red, not merely because of its motion, but because time in that region runs differently from the way our flat intuitions expect. Gravitational redshift is one of those ideas that sounds poetic until it becomes measurable. The phrase can make it feel like color with a philosophical accent. It is more severe than that. Light is a clock in motion. Its frequency is part of its identity. If radiation must climb out of strong gravity, the energy bookkeeping changes. To a distant observer, the light arrives with a longer wavelength, not because the source has become less real, but because space-time itself has imposed a cost on escape. The light has to pay to leave. And so the test became beautifully simple in concept, brutally difficult in practice. Watch S2 as it swings close to Sagittarius A star. Measure its spectral lines with enough precision to distinguish ordinary Doppler motion from the extra shift demanded by relativity. If Einstein is right, the light from the star should emerge carrying the mark of deeper gravity, not metaphorically, quantitatively. In 2018, during a key close passage of S2, that signature was observed. The star's light showed the expected relativistic redshift within the precision of the measurements. This did not prove Einstein in the grand naive sense. General relativity had already survived many tests. Science is not a religion of permanent finality, but it did something far more narratively important here. It demonstrated that the object at the center of the Milky Way was not only massive enough to command stellar orbits, it was embedded in a space-time structure harsh enough to make those orbits carry Einstein's imprint in their light. Sagittarius A star was no longer just the best explanation for a hidden central mass. It had become a laboratory where gravity itself was showing its deeper grammar. That is the midpoint turn in the entire story. Until now, the viewer could still imagine that this was about identifying a cosmic object, find the center, discover the source, weigh the darkness, infer the black hole. But once relativity enters through the orbit of S2, the topic grows larger than the object. The real subject is no longer just, what is Sagittarius a star? The real subject becomes, what kind of reality allows a star to carry warp time in its light? The center of the galaxy stops being merely a destination in space. It becomes a place where ordinary ontology starts to thin out. And the deeper measurements did not stop with redshift. Another prediction of general relativity concerns orbital precession. In a perfectly Newtonian description, an orbiting body on an ellipse would retrace the same path indefinitely if the system were isolated and idealized. In relativity, the ellipse itself slowly rotates. The point of closest approach drifts over time. The orbit does not close perfectly. It precesses. This effect was famously measured in Mercury's orbit around the Sun, one of the early triumphs of Einstein's theory. Near Sagittarius, a star, the same logic becomes more dramatic. The potential is deeper, the geometry more severe. The deviation from Newton should be more pronounced. And indeed, as observations continued, relativistic precession in S2's orbit became part of the emerging picture. This was not merely decorative confirmation. It changed the emotional meaning of the galactic center. The stars there were no longer just acting as test particles for an unseen mass. They were revealing that Newton's older, flatter picture of reality was no longer enough to describe what they were living through. That is the true violence of black holes. Not only that they gather matter, not only that they hide behind horizons, but that they force reality itself out of the comfortable language we use almost everywhere else. The orbit of S2 is therefore more than a measurement. It is a wound in classical intuition. A star races around an invisible center, yes. But it also does something stranger. It carries evidence that time and geometry near that center have become inseparable from gravity. The old division between where something is and when something happens begins to erode. Space is no longer just location. Time is no longer just flow. Near Sagittarius, a star. They begin acting like one compromised fabric, responding to a concentrated authority. The black hole does not merely bend trajectories. It bends the terms on which trajectories can be understood. This is where the psychological pressure deepens. People often imagine that science calms reality by explaining it, but there are subjects where explanation has the opposite effect. The more precisely we understand them, the less comfortable the world becomes. Sagittarius. A star is one of those subjects. Before the measurements, the galactic center could be romanticized as a dark mystery. After the measurements, it becomes worse than a mystery. It becomes lawful. Because law is harder to resist than legend. A legend can be dismissed, a story can be doubted, but when a star returns on a 16-year orbit, when its velocity climbs to thousands of kilometers per second, when its spectrum reddens in the way relativity demands, when its path subtly precesses in the geometry Einstein described, the unease matures. The center of the galaxy is not strange because we do not understand it. It is strange because we do understand enough of it to see that reality is built less intuitively than our minds require. That is the second ignition of the script. The first was discovering that the hidden center existed. The second is realizing that the center is not just hidden matter, but a place where the structure of space-time itself has become experimentally visible through the life of a star. And once that lands, another question opens beneath it. If gravity near Sagittarius, A star can alter time outside the black hole, if a nearby star's light has to climb through curved space-time to reach us, then what exactly does it mean to fall deeper still? What happens when the geometry is no longer merely strong, but terminal? What, in human terms, does it mean to approach a region where escape stops being a future the universe permits? Because measuring the orbit is one thing. Living inside the logic of that orbit is another. And that is where the black hole ceases to be a triumph of astronomy and becomes a direct assault on the way we think. Falling, seeing, and waiting are supposed to work. Because the moment you stop treating a black hole as a distant label and start asking what its geometry would actually do to experience, ordinary language begins to fray. We use words like falling, approaching, crossing, seeing, waiting as though they belong to a stable world. As though the meanings are fixed in advance. On Earth, and through most of the universe we casually inhabit an imagination. That works well enough. Falling means moving downward into a stronger gravitational field. Waiting means time passing in a shared sense. Seeing means receiving light from an event that happened somewhere else. Approaching a boundary means eventually arriving at it. These are not merely physical habits. They are psychological rights. We rely on them so deeply that they stop feeling like assumptions. Near a black hole, those rights are revoked one by one. Start with falling. In everyday life, falling feels like motion through space towards some destination. It is kinetic, directional, usually brief, and defined by a surface waiting at the end. Even orbital motion still preserves some of that intuition. A satellite falls around Earth. A planet falls endlessly around a star. The geometry is curved, yes, but the world remains legible. There is still an outside. There is still a meaningful distinction between descent and escape. Near a black hole, that distinction begins to corrode. Far away from Sagittarius. A star, gravity behaves in ways our instincts can still negotiate. Stars orbit. Gas moves inward or is flung outward. Light bends a little. But as you push closer, especially toward the event horizon, the geometry becomes so severe that falling in is no longer well described as moving through an ordinary environment toward an ordinary place. It is better understood as entering a region where the structure of possible futures narrows. The black hole does not merely pull you, it reorganizes what counts as a way forward. That is why the event horizon is so often misunderstood. People imagine a line in space, a bright ring, a final cliff edge, some visible marker of cosmic danger. But the horizon is not a painted border. It is a causal boundary. Once crossed, every future-directed path continues inward. Not because you lack courage, not because your engines are too weak, because the geometry no longer permits an outside future. This is a hard thing to feel, honestly, because the language we use still smuggles in flat space intuition. Inside sounds like being contained. Trapped sounds like being held back by a force. Even escape velocity can make the situation sound like a very steep hill. But the horizon is not steepness in the ordinary sense. It is a more radical rearrangement than that. It is what happens when outward ceases to be a survivable category of tomorrow. Inside, later points inward. That sentence is worth staying with, because it expresses something deeper than danger. It says that a black hole changes not just the difficulty of motion, but the meaning of direction itself. On Earth, you can choose to walk north or south, up a hill or down one, toward a door or away from it, near and beyond a horizon. That intuitive freedom is no longer represented in the same way. Your options do not merely shrink. The space-time structure underneath the options has changed. And then there is seeing. We like to think of vision as passive. Light arrives. The world reports itself. But black holes reveal how contingent that trust really is. Consider an object falling towards Sagittarius, a star. To the object itself, assuming the black hole is supermassive enough, the crossing of the horizon need not be dramatic at that exact moment. The tidal forces at the horizon of a supermassive black hole are much gentler than those near a small stellar mass one. Locally, the infalling traveler may notice no flash, no impact, no luminous threshold hanging in space. Physics does not owe you a theatrical warning. But to a distant observer, the story is different. As the object falls deeper into the gravitational well, the light it sends outward becomes increasingly redshifted. The intervals between received signals stretch. The object appears to slow, dim, and fade. In the limit, its visible approach to the horizon asymptotically stalls. It does not seem to crash through a visible boundary in any simple cinematic sense. Instead, it is gradually peeled away from observation, not because it ceases to exist, but because the light by which it announces itself is being taxed into irrelevance. The object continues. The image fails. This distinction matters enormously. A black hole is not merely a place where matter disappears. It is a place where visibility and physical process begin to separate. What is happening and what can still be seen happening no longer align in the comfortable way our minds expect. The world goes on. Observation loses custody of it. That is one of the most haunting lessons Sagittarius A star teaches. Reality does not promise to remain accessible at the same depth at which it remains lawful. And then there is waiting. Time dilation is one of those phrases that popular culture has made famous without making it psychologically habitable. It gets treated like a clever effect, a weird technicality, another science fiction flourish. But in the presence of a black hole, time dilation becomes less like a trick and more like a wound in simultaneity. Clocks deeper in a gravitational field run differently relative to clocks far away. This is not metaphor. It is built into the geometry, near Sagittarius A star, and near black holes in general. Time is not a single universal river carrying all observers equally. It is local, contingent, bound to trajectories and gravitational depth. Which means waiting is no longer shared. That alone should disturb us more than it does. So much of human sanity depends on the assumption that time is, if not perfectly identical for everyone. At least one thing in principle: a world, a background, a common stage on which different lives unfold. Relativity breaks that gently in everyday life and brutally in extreme gravity. Near a black hole, the difference between your time and someone else's is not philosophical bookkeeping. It is architecture. The deeper you go, the less the old collective intuition survives. This is where the human imagination often reaches for the word spaghettification, because it is vivid and grotesque and easy to remember. It refers to the tidal stretching caused by strong gravitational gradients, the difference in gravitational pull between one part of your body and another. Near a sufficiently small black hole, those gradients become lethal well before the event horizon, pulling feet and head with such unequal force that matter is stretched catastrophically. Near a supermassive black hole like Sagittarius A star, that exact effect at the horizon is far less immediate. The horizon can be crossed before tidal forces become violently destructive. The black hole is so large that the local gradient at the horizon is not yet terminal in the same way. That fact is not comforting. It makes the black hole stranger, not kinder. Because it means the decisive transition is not necessarily the moment pain begins. It is the moment escape ends, whether or not sensation has caught up to the significance. We are used to reality warning us through feeling, fire burns, pressure hurts, impacts announce themselves. A supermassive black hole can withhold that courtesy. The geometry can become fatal before the body has a dramatic story to tell about it. The catastrophe is first structural. Only later does it become anatomical. And this brings us back to Sagittarius A star with a sharpened understanding. When we say that the center of the Milky Way contains a supermassive black hole, we are not just saying there is a very dense object sitting there in the dark. We are saying that at the heart of our galaxy is a region where the relationship between light, time, motion, and causality has been driven into forms that ordinary experience cannot rehearse. A place where a star like S2 can carry warp time in its light. A place where the distinction between what an infalling traveler experiences and what a distant observer sees becomes unavoidable. A place where falling in eventually ceases to mean moving toward a thing and starts meaning being absorbed by a future you cannot turn away from. The black hole does not simply trap matter. It traps the grammar of ordinary experience. That is why black holes remain so disproportionately powerful in human thought, even among people who never learn the equations. Somewhere beneath a popular mythology, there is an accurate instinct trying to speak. The black hole frightens us not merely because it is destructive, but because it reveals that the world is built from rules more severe than the ones our perception teaches us. It takes categories we trust without noticing, near and far, now and later, seen and unseen, approaching and arriving, and shows that under enough gravity, they begin to come apart. And yet there is another turn here, one no less strange for being quieter. Given everything a black hole is, given everything Sagittarius, A star appears to be, one might expect the center of the Milky Way to blaze continuously with the violence of matter pouring inward. One might expect a supermassive black hole of 4 million solar masses to feed conspicuously, to roar in X-rays, to flood the inner galaxy with the unmistakable signature of an active monster at work. But Sagittarius A star does not behave that way most of the time. It flickers, it flares, it whispers. By the standards of the most luminous galactic nuclei in the universe, it is strangely subdued. And that may be the next insult to intuition. Because after all this buildup, after the hidden mass, the ruthless compression, the orbits, the relativistic light, the collapse of ordinary categories, you arrive at a black hole powerful enough to organize the center of a galaxy, and discover that it is, in a very real sense, almost starving. Power, once again, refuses to look the way we think it should. That is one of the most beautiful reversals in the entire story. After everything Sagittarius A star has forced us to accept, the hidden center, the crushed scale, the stars racing around an invisible master, the light of S2 carrying the signature of warp time, you would think the next step would be obvious. A supermassive black hole at the center of the Milky Way should be a furnace in permanent overdrive. It should be swallowing matter with theatrical appetite. It should blaze so fiercely that the inner galaxy feels less like a stellar city and more like the mouth of an engine. Sometimes the universe does behave that way. There are galaxies whose central black holes feed so aggressively that they outshine the combined starlight of the galaxies around them. Quasars and active galactic nuclei are among the brightest sustained phenomena in the cosmos. Gas falls inward, heats through friction and compression, forms a rotating accretion flow, and radiates across the electromagnetic spectrum. In those moments, the black hole does not shine by itself. The horizon remains dark, but the matter losing orbital freedom around it can become incandescent. An active black hole can turn infall into a spectacle visible across cosmic distance. By that standard, Sagittarius A star is oddly restrained. It is not silent. Silence would be simpler. It emits in radio. It flickers in infrared. It produces X-ray flares. It is unmistakably there. But for a black hole with more than 4 million solar masses, the overall luminosity is astonishingly low. It is underfed, underluminous, almost embarrassingly modest compared with the brilliant central engines seen elsewhere in the universe. That should not calm us. It should unsettle us further. Because this is not the silence of weakness. It is the silence of a structure that does not need constant display to remain decisive. Sagittarius. A star dominates the center of the Milky Way, whether or not it is visibly feasting. Its authority is gravitational first, radiative second. The black hole does not need to perform its power continuously in light for that power to organize the region around it. Once again, reality refuses the easy visual story. The natural question, then, is why? If a supermassive black hole sits in the middle of a galaxy, with stars all around it and gas moving through the central regions, why is it not glowing far more violently? Why is our galactic center not a miniature quasar? The answer begins with something deceptively simple. Matter has to do more than exist nearby. It has to lose enough angular momentum to fall inward efficiently. That is a much harsher requirement than casual intuition suggests. Orbit is not a prelude to falling. Orbit is often what prevents falling. Gas, dust, and stellar winds in the galactic center can all supply material to the environment around Sagittarius, A star. But reaching the immediate vicinity of the black hole is only part of the problem. To continue inward, matter has to shed energy and angular momentum through turbulent, magnetic, and collisional processes. Some of it does. Much of it does not do so efficiently enough to create the kind of bright, orderly accretion disk seen in the most luminous active nuclei. That inefficiency changes everything. In the brightest quasars, accretion is radiatively efficient. A substantial fraction of the gravitational energy released by infalling matter is converted into outgoing radiation. The system shines because the flow is dense and organized enough for heat and light to escape before the matter crosses the horizon. Sagittarius. A star appears to inhabit a very different regime. The gas around it is thin, hot, turbulent, magnetized, and inefficient at turning infall into sustained brilliance. Much of the energy can remain trapped in the flow, advected inward, or carried off in ways that do not yield the kind of luminous display our intuition expects. This is why astronomers often describe the environment around Sagittarius. A star using models of radiatively inefficient accretion flow. The phrase is technical, but the intuition behind it is stark. Matter can fall deep into gravity without advertising most of the process in light. The black hole can be fed just enough to remain active, just enough to produce flares and radio emission and a hot surrounding plasma, yet still remain comparatively dim when measured against what a 4 million solar mass appetite might seem to promise. Power does not always announce itself with brightness. That line matters here because it is easy to underestimate how conceptually destabilizing this is. In ordinary life, energy and visibility often travel together. A fire glows. A machine at full strain makes noise. Violence tends to mark its own presence, but black holes continue to erode that expectation. First, they taught us that the deepest mass concentration in the Milky Way could remain nearly invisible. Now, Sagittarius. A star teaches that even a supermassive black hole can interact with its environment in ways that remain physically important while looking, by comparison with brighter cousins, almost restrained. The underfed black hole is not a contradiction in physics. It is a contradiction in instinct. Still, the quiet is not absolute. Sagittarius. A star flares, sometimes in X-rays, sometimes in infrared. These flares are brief and variable, like sparks from a machine mostly hidden behind its casing. Their exact microphysics is still an active area of research, but they are commonly linked to turbulent processes in the hot plasma close to the black hole, including magnetic reconnection and the acceleration of electrons to high energies. In simpler terms, the environment near Sagittarius, a star is not placid. It is restless, intermittent, unstable on short time scales. Energy can build, twist, release. The black hole may be underfed by quasar standards, but the region around it is still alive with small acts of violence. This is important because low luminosity should not be mistaken for emptiness. Dimness is not dormancy. Sagittarius. A star is not a sleeping object in the naive sense. It is more like a powerful engine idling irregularly, with only occasional flashes exposing how much structure remains hidden in the dark. One of the most publicized moments in this line of inquiry involved a cloud-like object known as G2, which approached Sagittarius A star on a plunging orbit. There was intense interest in whether this encounter would trigger dramatic brightening as material interacted with the black hole's environment. The event became a kind of natural experiment in public view. Would the central black hole suddenly awaken in obvious fashion? The outcome was more restrained than many dramatic expectations had imagined. The interaction proved interesting, but it did not transform Sagittarius A star into a blazing central beacon. That result is worth dwelling on, because it reveals something about both the black hole and us. We keep expecting visible drama. We keep expecting the center to confess itself in the language of spectacle. But Sagittarius A star keeps resisting that demand. It is massive enough to dominate, relativistic enough to bend time, compact enough to annihilate most alternatives, yet in its feeding behavior, it remains frustratingly economical. It gives us flickers instead of declarations. It reminds us that the universe is under no obligation to package importance in a form that flatters the eye. There is also a deeper physical lesson here. A black hole's luminosity tells you not simply how massive it is, but how matter is behaving around it right now. Mass is a statement about what the object has become. Brightness is often a statement about current supply and current process. The two can diverge dramatically. A black hole may have grown through earlier epochs of far greater activity and now live in comparative austerity. In that sense, Sagittarius A star may be quiet not because it was always quiet, but because we happen to inhabit a relatively subdued chapter in its long biography. That possibility opens the story outward. Because once you accept that Sagittarius A star is presently underluminous, you begin to wonder what the larger central environment is actually like. What gas is available there? How crowded is the region? How many stars are packed into the central cluster? What old outbursts may have happened before humans existed to witness them? How much latent violence can accumulate in a place where the black hole itself seems almost restrained, but the surrounding ecology is dense, hot, and unstable? The galactic center is not just a black hole with empty space around it. It is an ecosystem. Stars orbit there at terrifying speeds. Stellar winds collide. Gas clouds thread through the region. Radiation fields overlap. Magnetic structure matters. The black hole sits inside that environment, not as a theatrical devourer in constant public performance, but as the central pressure around which an entire brutal ecology has learned to organize itself. And that is the next step the story demands. Because if Sagittarius A star is not continuously announcing its power by feeding at quasar levels, then the real character of the galactic center must be sought in the crowded environment around it, the stars, the gas, the cluster, the heat, the density, the historical traces of past activity. The center of the Milky Way is not just a point mass, it is a region where darkness has neighbors. And once you enter that region, even the word night starts to lose its meaning. It is easy, from far away, to imagine a black hole as an isolated sovereign. A dark object, a clean center, empty space around it, gravity doing its work in silence. The actual center of the Milky Way is nothing like that. Sagittarius. A star does not sit in a void. It sits in congestion, in pressure, in a region so crowded with stars, gas, dust, radiation, and magnetic structure that the word environment starts to feel too mild. This is not a lonely abyss in deep space. It is a compact, urban core of the galaxy, a place where matter has been piling up, colliding, heating, orbiting, and remembering gravity for billions of years. If the black hole is the central fact, the surrounding region is the proof that facts this deep are never alone for long. That matters, because a black hole is easiest to misunderstand when it is imagined in isolation. The center of the Milky Way is not merely a black hole story. It is a black hole embedded in an ecology. An ecology changes tone. The space around our sun feels spacious by everyday galactic standards. The nearest star is more than 4 light-years away, in the central regions of the Milky Way. That kind of separation becomes a luxury. The nuclear star cluster surrounding Sagittarius. A star is one of the densest stellar environments in the galaxy. Millions of stars are packed into a region only a few parsecs across. Not a vague haze, but a genuine crowding of suns, stellar remnants, gas structures, and orbital histories all layered into the same compressed domain. If you could stand there safely, and you cannot, the sky would no longer resemble anything the word sky was made for. Night would lose its darkness first. There would be stars everywhere, but not as a gentle backdrop. They would hang in impossible densities, some near, some brighter, some moving in ways that would make our local celestial order feel provincial and fragile. The black spaces between points of light would shrink. Radiation would not feel like something arriving from distant objects across polite emptiness. It would feel ambient, local, almost infrastructural. The galactic center is not merely bright. It is crowded enough to make emptiness itself feel scarce. And the crowd is not static. Stars there are not sitting in a peaceful arrangement around Sagittarius, a star-like respectful audience members around a stage. They move through one another's gravitational influence. Some form in clusters. Some are scattered by encounters. Some die and leave compact remnants behind. Stellar winds from massive stars stream outward and collide, injecting energy and material into the environment. Gas clouds are heated, torn, ionized, threaded by magnetic fields. The region behaves less like an astronomical postcard and more like a densely loaded machine in which almost every component is pushing on something else. That is why the black hole's current low feeding rate can be so misleading if taken alone. The center is not quiet because it lacks fuel. It is quiet in a more nuanced way. The available matter is not organized into the kind of smooth, dense, radiatively efficient inflow that would turn Sagittarius A star into a quasar. But fuel exists, motion exists, turbulence exists, violence exists. The ecology around the hole is active even when the hole itself is not publicly feeding at its brightest. This central stellar population includes young, massive stars that are themselves an ongoing puzzle. In a region where tidal forces from the black hole are strong and conditions are extreme, one might not expect star formation to be straightforward. And yet, massive young stars are there. Their presence forces astronomers to ask uncomfortable questions about how stars can form or be driven inward in such a harsh gravitational setting. Even the stellar demographics of the galactic center refuse to remain simple. That is a pattern now. Every time intuition tries to settle, the center produces another complication. Even the distribution of stellar remnants matters here. Over long time scales, dense central environments should accumulate white dwarfs, neutron stars, and stellar mass black holes. Gravity sorts. Encounters reshuffle. Massive bodies can drift inward through dynamical processes. The result is that the region around Sagittarius A star is likely inhabited not just by luminous stars, but by a hidden population of darker, denser objects that add further complexity to the gravitational and collisional ecology. The black hole dominates the overall potential in the immediate center, yes, but it does so inside a region where many lesser graves of stellar evolution may also be crowding inward. Darkness, here, comes in layers. And then there is the gas. Gas near the galactic center is not decorative background material. It is one of the main ways the region remembers and expresses its violence. Clouds of molecular gas drift through the inner galaxy. Ionized structures arc and stream near the core. Stellar winds from hot, massive stars pour energy into the medium, colliding and shocking against one another. Some of this material may eventually wander close enough and lose enough angular momentum to contribute to the black hole's intermittent feeding. Some of it forms rotating structures on larger scales. Some of it is heated, stirred, expelled, or trapped in turbulent circulation. In a region this dense, gas is not passive. It is the most mobile memory the environment has. One of the notable structures in the central few parsecs is the circumnuclear disk, a ring-like accumulation of molecular gas and dust surrounding the innermost region. It is not a neat, serene ring in the way the phrase might suggest. It is clumpy, dynamic, imperfect. But it matters because it marks the fact that the black hole's neighborhood is not empty, not bare, not reduced to stars alone. Sagittarius. A star lives inside a larger architecture of available matter, a potential reservoir not continuously consumed, but never wholly irrelevant. The center, in other words, is provisioned. That is part of what makes its current restraint so eerie. The region does not look starved in any simple cosmic sense. It looks crowded, heated, structurally loaded, yet the black hole remains comparatively dim. This mismatch between available environment and present luminosity gives the galactic center a kind of coiled quality, as though much of its significance lies not in what it is doing at maximum theatrical volume, but in what it is capable of under the right conditions. And capability matters more than spectacle. Because once you enter this ecology, the black hole begins to feel less like a lone object and more like the deepest term in a hierarchy of compression. There are stars, dense clusters, gas structures, compact remnants, radiation fields, all nested in rising degrees of crowding and consequence. Then, at the center of all of that, Sagittarius. A star sits as the final concentration, the place where the environment's accumulated logic reaches its most severe form. The black hole is not outside the ecology. It is the ecology's deepest sentence. That is why the atmosphere of the galactic center should not be imagined as a clean confrontation between matter and void. It is more intimate than that. Matter is everywhere. Heat is everywhere. Movement is everywhere. Even the darkness is busy. A star there does not live in a broad suburban galaxy like ours. It lives in a region where proximity itself becomes stressful, where orbits are tighter, encounters more consequential, and the central gravitational field always waiting beneath the rest, like a hidden legal code. There is a particular kind of pressure that comes from density, not the pressure of a single catastrophe, but of reduced freedom, fewer clean paths, less empty room, more interaction, more mutual influence. The center of the Milky Way feels like that, even in description. It is not just a location where extreme things happen. It is a location where matter has fewer ways to remain innocent. This is one reason the galactic center is such a powerful setting for science. It compresses many scales of astrophysics into one place: stellar evolution, gas dynamics, magnetic activity, relativistic gravity, orbital mechanics, high-energy radiation. They all overlap there. The region is a laboratory not because it is simple, but because it is unforgiving. The underlying structures cannot hide forever when so many processes are crowding one another into visibility. And yet, for all this activity, we are still living in a comparatively quiet chapter of the center's biography. That is easy to forget. A place this dense, with a supermassive black hole at its core and a loaded environment around it, does not need to have been quiet forever just because it is relatively subdued now. In fact, the ecology almost invites the opposite suspicion. If enough gas reached the hole in the past, if enough instability developed, if enough angular momentum was lost, the central engine could have entered much brighter phases. The current dimness may not be the identity of Sagittarius A star so much as its present mood. And the galaxy may still be carrying evidence of other moods. Because environments remember, gas can preserve shocks, clouds can preserve illumination, echoes. Larger galactic structures can preserve the aftermath of outbursts long after the source itself has dimmed again. The center may look modest today by quasar standards, but that does not mean the Milky Way has always had a quiet heart. The ecology around Sagittarius. A star is dense enough, provisioned enough, and unstable enough to make a deeper possibility hard to ignore. Perhaps the black hole is not revealing its true nature through what it is doing now, but through what the galaxy still remembers it having done. And once you ask that, the story changes again. The question is no longer only what lives at the center of the Milky Way. The question becomes what the Milky Way's center has already done to the galaxy, and whether the sky still carries scars from times when Sagittarius A star was far less restrained. And the galaxy does carry scars. That is one of the strangest emotional turns in this story. For a long time. Sagittarius. A star could be imagined as a present tense problem, a black hole sitting quietly at the center of the Milky Way, underfed, compact, powerful, but mostly restrained, a deep structure rather than a dramatic event. But galaxies are not creatures of the present alone. They archive. They preserve heat, shock, ionization, chemical aftermath, ghostly illumination. They let old violence linger in matter long after the central engine has dropped its voice. Which means the quiet black hole we see today may not be the whole character of Sagittarius A star. It may only be the latest expression. This is where the biography of the galactic center opens beyond direct observation and becomes something more haunting, an investigation of things that happened before anyone was here to see them, but not so completely erased that the universe failed to keep a record. One of the most dramatic records sits on a scale so large that it almost feels disconnected from the compact darkness at the center. The Fermi bubbles. Discovered through gamma-ray observations, these enormous lobes extend above and below the plane of the Milky Way, reaching tens of thousands of light-years into the galactic halo. They are not small local disturbances. They are galactic-scale structures, immense paired outflows or inflated regions of energetic material rising from the central parts of the galaxy, like the frozen aftermath of some old release. Their edges are relatively sharp. Their symmetry is too suggestive to ignore. They appear to know where the center is. That is the unnerving part. A galaxy-wide structure is one thing. A galaxy-wide structure aligned with the central engine is another. The bubbles are not proof, by themselves, of one single simple event. Science here has to remain careful. There are multiple ideas about their origin, including activity tied to Sagittarius A star and large-scale star formation episodes near the galactic center. Some models emphasize outflows driven by the supermassive black hole during a brighter accretion phase. Others consider the collective effect of stellar processes in the central regions. The precise balance is still actively studied. But what matters for the deeper story is not false certainty. It is the narrowing of innocence. The Milky Way is not behaving like a galaxy whose center has always been perfectly quiet. Something injected energy on a vast scale. Something shaped the halo in a way that points back toward the central regions. And once you know a supermassive black hole lives there, even a relatively subdued one in the present, the possibility becomes difficult to ignore that our galaxy's center may have experienced brighter, harsher episodes in the past. Not quasar level on the most extreme cosmic scale, perhaps, but still far more active than what we witness now. That possibility changes the tone of Sagittarius A star immediately. The black hole is no longer just a silent authority holding the center together. It becomes a historical actor, a thing whose present quiet may conceal a more violent archive. And the evidence for that possibility is not limited to the giant structures far above and below the galactic plane. There are also subtler records, closer in, written not in shape alone, but in delayed light. Certain molecular clouds near the galactic center have shown X-ray emission consistent with the idea that they were illuminated by a stronger source in the recent past. The basic logic is beautiful in a severe way. A bright outburst from the central region sends radiation outward. Some of that radiation encounters distant clouds, is absorbed, reprocessed, re-emitted. Because of light travel time, the echo reaches us later, from a different path, as though the galaxy itself were answering a question too late for us to have heard it asked directly. The cloud glows after the center has already gone quiet. That is one of the few ways the universe lets you study vanished brilliance, not by preserving the event itself, but by letting distant matter continue reacting to it after the source has changed state. These X-ray reflection nebulae do not provide a perfectly cinematic replay. They are not a direct recording in the human sense. Interpreting them requires care, geometry, modeling, assumptions about cloud structure and illumination history. But the broader implication is powerful. The galactic center appears to have been brighter in X-rays within the past few hundred years to few thousand years than it is now. Not in the deep geological sense of long ago, but in a time frame almost offensively recent by galactic standards. Recent enough that the quiet heart of the Milky Way begins to feel less like a stable identity and more like a temporary posture. That should alter the viewer's internal model of the black hole. Sagittarius. A star is not a static monument. It is a variable engine living inside an evolving environment. Give it more fuel under the right conditions, and its radiative character changes. Let the inflow drop, and the engine falls back toward comparative austerity. Its mass remains, its horizon remains, its gravitational authority remains, but the visible and high-energy signature through which the wider galaxy experiences that authority can shift dramatically across time. The black hole has moods. The galaxy remembers them. There is something almost anatomical about this. The Milky Way's center is not only a place where matter is compressed and time is bent, it is also a source of pulses, episodes, changes in metabolic intensity. Most of the time, in our era, the heart beats quietly enough that the rest of the galaxy is not overwhelmed by it. But every now and then, in history we can only partially reconstruct, it seems to have surged, and the body of the galaxy still carries the physiological consequences. That metaphor has limits. Of course, a galaxy is not an organism. A black hole is not alive. But the comparison earns a certain force here because it clarifies something real. The center does not merely exist. It acts, intermittently, on a scale larger than itself, and its past states remain legible in the material it has disturbed. This is part of why Sagittarius A star is such a powerful subject for long-form thought. It is not only the current object that matters, it is the layered relationship between current state and historical inference. What we see now is a subdued black hole. What the galaxy around it suggests is a richer, less restrained biography. The truth is not neatly visible in one image or one data set. It has to be assembled from scars, echoes, distributions, and asymmetries. Once again, the deepest fact is not given directly. It is reconstructed from what the center has forced everything else to remember. And that theme keeps intensifying. At first, we could not find the center directly because dust stood in the way. Then we found a compact radio source. Then stars exposed the hidden mass. Then relativity emerged in their motion. Then the black holes present under feeding complicated the expectation of visible power. Now, even the apparent quiet has turned out not to be simple. The center may be dim today, but the galaxy still bears evidence that dimness is not the whole truth of what Sagittarius A star has been. Each answer has opened into a larger discomfort. That is the correct shape of the story, because the real subject was never just the black hole as an isolated object. It was always the mismatch between what looks obvious and what is physically decisive. The center of the Milky Way keeps teaching the same lesson in new forms. That reality does not present its hierarchy on the surface. The deepest structures often have to be inferred from deformation, from memory, from delayed light, from obedience, from scars. The universe does not simply tell you what matters. It makes other things behave as though they know. And this is what finally pushes the narrative toward one of its most beautiful culminations. For all the orbital evidence, all the compactness arguments, all the echoes and scars, one desire remains almost embarrassingly human. To see it, not just infer it, not just weigh it, not just watch stars testify around it or clouds glow from its past moods. To look toward the center of the galaxy and produce something closer to an image, some visual reckoning with the hidden architecture we have spent so long reconstructing by indirect means. That desire is deeper than vanity. It is about closure, about whether a reality so heavily built from inference can ever be granted even a partial visual form. But black holes make even that wish difficult. Sagittarius. A star is not only hidden by distance and dust and the ordinary limits of instruments, it is also small on the sky in an almost offensive way. The event horizon-scale region subtends an angle so tiny that resolving it from Earth is like trying to see a glowing ring around a darkness from across the continent with a single eye. So, if astronomy wanted to see the center in anything like the right way, it was going to have to build an instrument equal to the insult. Not a larger telescope. A planet learning how to look as one machine. Because that is what the scale of the problem demanded. Sagittarius. A star is enormous in mass and microscopic in angle. That combination is one of the great insults black holes deliver to observation. The object dominating the center of our galaxy is not merely hidden behind dust, or buried in a violent environment, or defined by a horizon that emits no light of its own. It is also, from Earth, astonishingly small on the sky. The region that matters most spans only tens of microarc seconds. That is a unit so fine, it barely feels like language. It means that even an object with millions of solar masses, sitting at the center of the Milky Way, presents itself to us as something smaller in apparent size than intuition thinks a galaxy's central secret has any right to be. If you wanted to resolve structure on that scale with ordinary optics, you would need an impossibly large telescope. So astronomy did the next least impossible thing. It turned the Earth into one. This is the conceptual force behind the Event Horizon Telescope, and it is difficult to overstate how appropriate it is to the subject. For most of this story, Sagittarius A star has forced science away from direct, comfortable seeing and toward inference, patience, and reconstruction. When the time finally came to produce an image of the black hole's immediate environment, the method itself had to preserve that same spirit. There would be no single instrument staring plainly into the center. There would be an array of observatories distributed across the planet, linked through timing, calibration, signal processing, and brutal mathematical care, acting together through very long baseline interferometry. A global eye assembled from separation. That phrase matters because it mirrors the object. The black hole itself is known by the strain it imposes across distance. To see it, humans had to coordinate across distance with a precision that bordered on the unnatural. Very long baseline interferometry, or VLBI, works by recording incoming radio signals at widely separated observatories with exquisitely precise timestamps, often referenced to atomic clocks. Later, those recordings are combined so that the separation between telescopes effectively becomes part of the resolving power of the system. The farther apart the dishes, the finer the angular detail that can, in principle, be reconstructed. It is not magic, and it is not simple photography in the everyday sense. The sky is sampled sparsely, incompletely. Atmospheric fluctuations intervene. Calibration errors creep in. The image must be built from data whose meaning is not sitting on the surface waiting to be read. Once again, the deepest truth is reconstructed, not handed over. That is part of why the Event Horizon Telescope feels so thematically exact. To image Sagittarius A star, astronomy had to accept the same lesson the black hole had been teaching all along. Visibility is not a given. It is something earned by architecture. And architecture was only the beginning. Sagittarius A star is not as observationally polite as the black hole in M87, whose first famous EHT image appeared before Sagittarius. A star's M87's central black hole is vastly more massive, which means its characteristic timescales are longer. Its emitting structure changes more slowly. Sagittarius A star, by contrast, is much smaller in mass and therefore more restless in the immediate environment near the horizon. Matter whipping around close to it can vary on timescales of minutes. Imagine trying to photograph not just an object at absurd angular resolution, but one whose appearance is changing while you are still learning how to assemble the image. It is not merely far away. It is unstable on the timescale of seeing. That made Sagittarius a star a particularly cruel target. The black hole at the center of our own galaxy was closer than M87's. Yes, but closeness did not make it easier in the way intuition might expect. The gas and plasma around it evolve quickly. Interstellar scattering along the line of sight further complicates the signal. The data do not arrive as a neat picture, but as an immense problem in coordination, signal, integrity, and inference. You are trying to recover the silhouette imposed on light by a region defined precisely by the failure of light to escape, while the luminous material around that region shifts under the pressure of gravity and magnetized turbulence. This is what it means to take black holes seriously. Even the act of looking must become relativistically literate. The Event Horizon Telescope, therefore, was not just a telescope. It was a planetary experiment in synchronization. Observatories at high, dry sites around the world observed together at millimeter wavelengths, where resolution and penetrative ability could be pushed into the regime the problem required. Petabytes of data were recorded onto physical storage because the volume was too great for ordinary internet transfer. Hydrogen master clocks kept time with brutal fidelity. Correlators later combined the signals. Imaging teams used multiple methods and blind procedures to reduce the risk that expectation would simply paint a black hole-shaped story into ambiguous data. That caution is important. When the subject is this mythologized, rigor has to become almost defensive. The public wants a black hole image the way myth wants a face for its monster. Science, if it is honest, wants something harder, a result that survives skepticism even when the object is famous enough to tempt self-deception. And when the results for Sagittarius A star finally emerged, what they offered was both less and more than naive desire had imagined. Less, because the image was not a straightforward snapshot in the everyday sense. Not the black hole itself standing cleanly revealed, not a luminous portrait with theatrical detail. More, because what appeared was exactly the kind of evidence black holes allow. A bright, uneven ring of emission surrounding a darker central depression, the so-called shadow, consistent with the expected gravitational lensing and photon capture near the event horizon scale region. We did not photograph the black hole itself. We photographed the shape of what light is no longer allowed to do. That is one of the most precise emotional statements in the entire saga. A black hole remains faithful to its nature, even in the moment of apparent visual triumph. It refuses the direct concession. What the image gives us is not the object laid bare, but the effect of extreme gravity on surrounding radiation. Light from hot plasma near the black hole is bent, redirected, lensed into a ring-like structure. Some photons escape after taking tortured paths through curved space-time. Others do not. The darkness at the center is not a painted hole in an otherwise ordinary scene. It is the visible consequence of an invisible boundary and the geometry around it. Even the image is a lesson in absence. And yet that absence is not vague. It is measurable. The angular size of the shadow-like feature and surrounding emission is consistent with the mass independently inferred from stellar orbits. That convergence matters immensely. These are not two versions of the same data flattering one another. The orbit of S2 and its companions, measured over decades in infrared, already weighed the hidden central mass. The EHT image, built through global interferometry at millimeter wavelengths, approached the same central reality from another direction entirely. When those lines of evidence meet, the black hole interpretation stops feeling like a daring synthesis and starts feeling like the least escapable description of what the galactic center is. That is the beauty of mature evidence. It does not merely intensify one argument. It makes different arguments collide into the same fact. Still, honesty again matters at the edge. The image of Sagittarius A star is not the end of inquiry. It does not tell us every detail of the plasma flow, magnetic field structure, or instantaneous geometry of the emitting region. Models differ. Variability complicates interpretation. The exact relation between observed brightness patterns and the underlying dynamics remains an active subject of study. This is not failure. It is the correct shape of serious science. The image is a threshold, not a final possession. And that may be the most faithful ending to the visual quest. We wanted to see the black hole, but what we received was something more philosophically exact, a picture that confirms the hidden architecture without abolishing the depth of the hiddenness. Even when the center is imaged, it is imaged as a limit. Sight gets closer. It does not become sovereign again. That should remind us where this whole descent began. The most important object in the Milky Way was almost invisible, then it became inferable, then measurable, then dynamically overwhelming, then relativistically legible, then historically scarred into the galaxy around it, and finally, through a planet-sized instrument, it became partially visible in the only way a black hole can permit, as a ring of strained light around an authority that remains dark at the center. Which leaves one last question, and it is the most important one. After all the proof, all the engineering, all the years of watching stars submit and light bend and data cohere, what has Sagittarius A star actually taught us about reality itself? What it has taught us, above all, is that proof does not restore comfort. That matters, because there is a common fantasy buried in the way people talk about science. First, something is mysterious. Then science arrives, measures it, explains it, images it, and the mystery is supposed to shrink into manageable knowledge. The world becomes clearer, and clarity is assumed to be soothing. That story works often enough to feel natural. It just does not work here. Sagittarius. A star has become one of the best established black holes in the universe. We know there is a compact object of about 4 million solar masses at the center of the Milky Way. We have tracked stars moving under its rule. We have seen relativistic effects in their motion and light. We have reconstructed an event horizon scale image consistent with extreme gravitational lensing around a dark central region. We have evidence that the galaxy still carries marks of stronger activity in the past. On paper, this is a triumph of explanation. And yet the cumulative effect is not reassurance. It is a colder kind of clarity. Because every layer of confirmation has reinforced the same unwelcome principle. The deepest structures of reality are often least available to the senses that made us feel at home in reality to begin with. Sagittarius. A star did not become less strange when it was measured. It became less avoidable. The black hole sits at the center of our galaxy as a case study in how lawful things can still be psychologically hostile. The image itself crystallizes that tension. When the Event Horizon Telescope result for Sagittarius A star was released, many people naturally treated it as the final visual payoff, the moment the hidden center had at last stepped into sight. But the image is more interesting than that, and harsher. What it gives us is not transparency. It gives us a ring of emission shaped by the tortured paths of light in curved space-time, wrapped around a central darkness where light is no longer behaving in ways ordinary vision can recover. The shadow is not a photographed surface. It is the visible signature of an invisible prohibition. The black hole is still keeping its terms. That is why the image feels so unlike a conquest. If you sit with it honestly, it is evidence of success, yes, but it is also evidence of limit. We have not forced the center to become simple. We have learned how to read simplicity out of a structure that remains fundamentally severe. The dark central region does not say, "Now you can see me." It says, "Now you can better understand why seeing was never going to be enough." This is what makes the convergence of evidence so philosophically heavy. The stellar orbits gave us mass. Relativity gave us geometry. The radio source gave us localization. The surrounding ecology gave us context. The past outbursts gave us biography. The EHT image gave us event horizon scale structure. Each method approached from a different angle, and each angle reduced the amount of interpretive mercy left to us. By the time they aligned, the real achievement was no longer simply identifying a black hole. It was learning how many layers of reality can agree while remaining resistant to ordinary appearance. The visible world is not the whole court of appeal. That is the sentence Sagittarius. A star keeps forcing through every method that touches it, and once you accept that, the center of the Milky Way begins to feel less like a destination in astronomy and more like a lesson in ontology. Not an argument that reality is unknowable. Almost the opposite. Sagittarius. A star is not unknowable in the lazy mystical sense. It is knowable through discipline, through mathematics, through years of patient measurement, through instruments that extend perception beyond biology, through a willingness to let indirect evidence carry more weight than familiar images. The unsettling part is that this path to knowledge does not preserve the old emotional contract. It does not promise that what is most real will look most obvious. It does not promise that explanation will make things feel more natural. It does not promise that deeper truth will be easier to live with than surface appearance. In fact, Sagittarius A star suggests the reverse. The deeper the truth, the less intuitive the world becomes. That is the mature form of the hook. We began with the idea that the most important object in the Milky Way is almost invisible. Now the thought has widened into something more difficult. Some of the most decisive things in the universe may be physically undeniable and yet permanently resistant to the kinds of presence our nervous systems were built to trust. Reality is not obliged to wear its hierarchy on the surface. It can hide its center behind dust, behind dynamics, behind curved time, behind dark boundaries, and still remain perfectly lawful all the way down. There is another consequence here. and it concerns humility. Not the decorative humility people perform when they say the universe is vast and we are small. A sharper humility. The kind that comes from realizing that human intuition is not just limited in scale, but locally trained on a very special neighborhood of reality. We evolved in weak gravity, low velocities, moderate temperatures, and middling densities. Our intuitions about time, space, cause, motion, and sight were shaped in a narrow band of conditions. Sagittarius. A star is what happens when those intuitions are forced into a domain that owes them nothing. The black hole is not irrational. We are provincial. That distinction is one of the most valuable things science can teach, and black holes teach it without gentleness. The center of the Milky Way is not a chaos point where law collapses into mystery. It is a place where law becomes more exact than intuition can comfortably escort. The black hole's darkness is not a failure of the universe to make sense. It is a failure of our default sensory expectations to remain sufficient. And still, the story does not end in despair. That matters too. It would be easy to push this into a cheap existential bleakness. Sight fails, intuition fails. The universe is hostile. End of story. But the actual shape is more interesting and more beautiful than that. We are creatures whose inherited perception was not built for the center of a galaxy, and yet we learned how to find it. Not perfectly, not completely, but enough to weigh the darkness, enough to watch stars mark its authority, enough to see light warped around its absence, enough to infer its history from scars the galaxy still carries. There is no comfort guarantee in that achievement, but there is dignity. We did not bring the black hole down to the level of instinct. We learned how to climb beyond instinct. That is a different kind of triumph, and a rarer one, not making reality resemble us, but extending ourselves just far enough to meet a reality that does not. Seen this way, the image of Sagittarius A star becomes almost ceremonial, not because it is a final portrait, but because it marks the threshold where human inquiry touched something near the center of our galaxy and managed, for an instant, to recover the shape of its invisibility. A ring of bent light around a dark gravitational claim. A visual statement that what cannot be seen directly can still be made legible by the damage it does to the ordinary behavior of the world. And if that is true at the center of the Milky Way, it raises a larger thought that reaches well beyond black holes. How much of reality, even outside these extreme environments, is structured that way? How often do we mistake visibility for importance? How often do we trust appearance simply because our species had to survive on appearance? How many of the world's deepest laws are not hidden in the sense of being secret, but hidden in the sense of requiring more patience, more indirection, more disciplined surrender than instinct likes to give? Sagittarius. A star may be an extreme object, but the epistemic lesson it teaches is not confined to extremes. The universe is full of things that must be known through consequences first. Fields, curvature, entropy, quantum states, dark matter. If it exists as current evidence strongly suggests, even the interiors of stars. Again and again, nature asks the same hard price. Stop treating the visible surface as the final form of the real. At the center of the galaxy, that lesson just becomes impossible to ignore. And that is why the black hole remains with you after the data, after the image, after the explanations. Not because it is a monster lurking in the dark. That is a childish version of the story. It remains because it reorganizes your sense of what it means for something to be real. Sagittarius. A star forces a change in emphasis, from appearance to effect, from sight to structure, from intuition to law, from the visible object to the hidden architecture that compels everything else around it. The deepest thing in the Milky Way does not shine in order to count. It counts first. The shining things reveal it afterward, which leaves only one place for the story to end. Not with the black hole as an object, but with the changed way of seeing it leaves behind. Because after all this, the center of the galaxy is no longer merely a point on a map or a famous astronomical source. It has become a lens through which the rest of reality starts to look different. And once that happens, even the night sky over Earth loses some of its innocence. Because once you know what is actually sitting at the center of the Milky Way, the sky stops being a backdrop. It becomes a disguise. The pale band of the galaxy stretching over a dark horizon can still look serene. It can still feel ancient, silent, almost merciful in its distance. Nothing in the naked eye image warns you that buried inside that glow is a compact darkness weighing more than 4 million suns. Nothing in the visual surface tells you that stars near the center are spending their lives in violent obedience. That time itself runs differently in that gravitational regime, that the galaxy may still carry scars from brighter outbursts in its past, or that an object defined by the failure of light can nevertheless be made visible through the deformation it imposes on everything around it. The eye gives you beauty. The structure gives you the truth. And Sagittarius A star is what happens when those two stop agreeing. That, in the end, is the real significance of the black hole at the center of our galaxy. Not simply that it exists, not simply that it is massive, or relativistic, or historically variable, or now partially imaged by a planet-sized instrument. The deeper significance is that it teaches a harder definition of reality. It forces us to accept that what is physically fundamental may remain visually recessive, that what governs a system may not announce itself at the surface of the system, that the deepest truths in nature are often not hidden because they are mystical, but because they are legible only to a mind willing to trust consequence over appearance. This is a more difficult kind of wonder than the cheap version. The cheap version says the universe is amazing because it is big, strange, and full of spectacular things. The harder version says the universe is amazing because it is lawful in ways that repeatedly outgrow the intuitions we use to feel at home inside it. Sagittarius A star belongs entirely to the harder version. It is a lesson in hidden structure, in disciplined inference, in the humiliation of sight, in the way gravity can become not just strong, but conceptually invasive, reaching into time, visibility, causality, and the meaning of direction itself. It is a reminder that understanding does not always simplify the world emotionally. Sometimes it does the opposite. Sometimes knowledge removes the comforting false picture and leaves you with something colder, cleaner, and more beautiful in a severe way. A galaxy with a bright center would have been easier on the nerves. A galaxy whose deepest anchor remained nearly invisible until stars, light, and mathematics gave it away is more truthful. That is why Sagittarius A star lingers after the facts have finished. Not because it is a cosmic villain, not because it is a tidy symbol of mystery, but because it permanently alters the relationship between what seems obvious and what is real. Once you understand how the center of the Milky Way was actually found, through dust, through radio whispers, through compressed mass budgets, through the orbit of S2, through Einstein written into starlight, through the ecology of the inner galaxy, through scars of older violence, through a ring of bent light around a dark constraint, you cannot quite return to the old faith in appearance. You begin to suspect that reality's deepest loyalties are elsewhere. And that suspicion is not paranoia, it is maturity. The world we evolved to navigate is a thin local layer of the world that actually exists, good enough for stone, weather, prey, shelter, sunrise, distance, danger, good enough for weak gravity and moderate speeds, good enough to build civilizations before relativity, quantum theory, radio astronomy, interferometry, and the slow violence of decades-long measurement taught us otherwise, but not good enough to look at the center of a galaxy and immediately know what rules it. For that, we had to become stranger than our senses. We had to learn to hear in wavelengths the eye cannot see, to trust orbital curves more than brightness, to let equations outrank intuition, to accept that a dark region in an image can be more informative than a luminous one, to build instruments that extend perception until biology is no longer the measure of the real. That is the human part of this story, and it deserves to be stated carefully, not as sentimental triumph and not as self-congratulation, but as a fact almost as surprising as the black hole itself. A species born in the outer suburbs of one ordinary galaxy learned, slowly and with many corrections, how to infer the hidden engine of its center. We did not do it by making the universe resemble us. We did it by surrendering, piece by piece, the assumptions that made us feel central, comfortable, and visually secure. We found the galactic center by giving up the fantasy that truth should look obvious. That may be the most valuable lesson Sagittarius A star offers. Because once that lesson sinks in, it spreads beyond black holes. It reaches into the rest of physics, the rest of astronomy, perhaps even the rest of serious thought. How often does the visible world flatter us with a surface account that is locally useful and globally incomplete? How often does explanation require us to distrust first impressions, not because first impressions are worthless, but because they are adapted to survival, not to final structure? How often do we mistake what is easy to picture for what is fundamental? At the center of the Milky Way, that mistake becomes unbearable. The thing that matters most, there does not shine. The thing that organizes the region is not the brightest thing in the region. The thing that is hardest to see is the thing the surrounding stars know most intimately. The most decisive reality is revealed not by its face, but by the obedience, distortion, and memory it leaves in everything else. That is not just a lesson about one black hole. It is a lesson about the architecture of the world. And so, the story returns, at last, to the image it began with. The galaxy arching overhead, calm to the eye, ancient in silence, its central light diffused by distance and dust. On the surface, nothing has changed. The Milky Way still looks the way it always looked to human beings before radio telescopes, before adaptive optics, before the Event Horizon Telescope, before anyone knew the name Sagittarius, a star. But knowledge has changed the surface without touching it. The night sky is still beautiful. It is simply no longer innocent. Somewhere inside that pale river of stars is a darkness so compact that it can bend time, command suns, and teach the visible universe to betray its presence. Somewhere in that brightness is a region where seeing fails before law does. Somewhere in that familiar band is the proof that reality can remain elegant, measurable, and brutally non-intuitive all at once. And perhaps that is the final realization. The lesson of the galactic center is not that darkness hides reality. It is that reality is often deepest exactly where sight fails. Not because the universe is withholding itself, not because knowledge is impossible, but because the world is built on structures more fundamental than appearance, and the price of meeting them is the surrender of whatever in us still expects truth to arrive already shaped for human eyes. Sagittarius A star is not the end of that lesson. It is simply one of the clearest places we have ever found it. A nearly invisible center, a 4 million solar mass absence, a darkness that does not need to glow in order to rule, a wound in intuition at the heart of our own galaxy. And once you know that, the Milky Way above you no longer feels like a picture. It feels like evidence,